So I'm Showman Lehiri, and I have been signed up to give this talk by Eric. And I think the title of the talk...
Professor of...
Oh, those things are unimportant. I work at NC State Department. Anybody who is interested can find more about that from the webpage. So mathematics of unevenly spaced time series. I think the word mathematics probably drove away most of the regular attendees. But so I'll hide behind that title too when I present this talk. In the sense there will not be almost no picture of galaxies, stars. It's more, if there is a picture, that would be of some likelihood and stuff. All right. So let's get started. So for time series, we are interested in unevenly spaced observations. But by time series, what we mean, it's again a stochastic process. That means we have a collection of random variables defined on the same probability space. And we can have discrete indices, time points 1, 2, etc., at which we collect the observations. Or we may have a continuous process indexed by t over some interval t. This is supposed to be the same in any case. While what we are trying to observe, they may evolve in continuous time. Our observations are always going to be at finitely many points. So these are discrete samples coming from either this continuous or something that already has a discrete structure. So before we get into unevenly spaced, perhaps we need to look at when, if you are given time points t1, t2, tn, when is it reasonable to assume that the underlying process is supported on this integer grid? And so when we are looking at t1, t2, tn, the potential points at which you can take observations, if you can embed them into a lattice like this, there is a common distance delta, and multiples of that will essentially cover t1 through tn. In that case, it's sensible to again model your underlying process as a discrete parameter process. And when that is not the case, you should be working with xt, where t runs over an interval, for example. And why do I care to separate these two cases? The reason will become clear in a moment. But before I go to the next slide, if we have a representation like this, we'll suppose that we have chosen the unit of time in such a way that delta is equal to 1. So x of k would be just that continuous process at time point k. K is an integer. So in the case when we have a discrete underlying process, these sampling locations, they are going to be a subset of z. Z is the set of all integers, plus, minus, etc. And what we can hope, we can only learn about characteristics of this discretized process. We have no hope of learning about the continuum. That's not possible. So in some sense, having these time points on the integer grid, that helps. Things are a little easier structurally, but the amount of information that you can extract is also going to be limited by that condition. For example, if you are looking at the second order characteristic like the autocovariance function, and if you suppose that this underlying discrete process is stationary, then our target function would be something like the covariance between x of t and x of t plus h. And this really doesn't depend on t, so this is just a function of h. And you might want to learn about the autocovariance function there, supported on h running over z.
xt is the temporal process, not the time series process, right? Like the time process, not the...
This one?
Yes.
xt?
XT, XS. Or the observation made at time t.
No, this is about the underlying process. I am not talking about, so these functions are defined for the underlying discrete process.
I see.
Okay, and we are supposed to, again, estimate or do inference on these based on x of t1 through x of tn.
Okay.
Yeah. All right. The other end of the spectrum, so we have this continuous time process t1, t2, tn. They need not be restricted to the set of all integers. They can take any possible value in the index set capital T. And again, if these cannot be embedded in a predetermined regular lattice, so in such cases, this continuous version of the process is important. And we can again hope to learn about not only the covariance between x of t and x of t plus h when t and t plus h are restricted to the set of all integers, but for any real numbers. So I put a silly question, the first one. What is the relation between this gamma h that I have defined here and the little gamma h that was defined there? Supposing I have conceptually a process that is defined on the continuum on all of the real line.
So for irregularly spaced data, x of t exists, but x of t plus h may not exist.
That is correct.
So-
But h here is a real number.
Okay, so then it always exists, but then
Only
it's
for the
not
pairs.
in discrete. H is real.
H is real. So only for pairs of differences,
So
ti
only
minus tj,
one pair contributes
perhaps.
to every value of capital gamma.
That's correct. That's correct. And only there are n choose too many such distances you can read out from the data. But I am not talking about estimation at this stage. Just look at the functions. In one case, it is defined for all h on the real line. In the other case, I am looking at only the definitions when I restrict h to the integers. So, as I said, the first question is silly. Yeah. So,
Stationary distribution, these two are equal, right?
yeah, I am assuming I have a continuous process, continuous parameter process, and so I can define both gamma of h and capital gamma of h for all h in R, in which case the restriction of this function to z will give me little gamma h. I just read out from this whole function on the real line, that is capital gamma of h, what happens only at the integer time points. As simple as that. So that's why I said it's silly. This is just something that is appearing here only for certain values of h. But now when you look at the spectral densities, there is some difference, right? So how do the spectral densities compare? So for this, I am going to again suppose that these are decaying fast enough as h goes to plus minus infinity. So it's absolutely summable. When you're looking at these quantities or when you integrate this, you get something finite. So it's short range dependent processes. So the spectral density for this one, if you have that summability condition, F is going to change to phi later on, but at this stage we don't have a competitor. So F is going to be what? 1 over twice pi. You can look at e to the power, or because this is symmetric, gamma of h and gamma of minus h, they're the same. Something like this, right? Again, I'm supposing this is finite. So that's how you can define the spectral density of a process that is defined on the integers. And when you look at the continuous case, so this T is 1R, something similar. I am not going to use H, change it to T. dt. It goes from minus infinity to plus infinity. Right. So in one case, you have a function that is defined only on a bounded interval, minus pi to plus pi, and this one is defined on R. And there is a relation between these two. So if you look at these two formulas, I should perhaps write capital gamma. That's what the notation says. And at integer time points, capital gamma of h would be little gamma of h. They're the same. Okay. The relation between these two, you can write down again by expressing gamma h in terms of this or that. So you are going to have to fold this to get that. Let's see. It's kind of strange, but it is true. I am drawing something that is corresponding to the normal distribution. So the PDF and the characteristic function, they'll have similar sort of structure, right? So if I think of this as my gamma, little gamma at each of these integer points, these are the values of this function. That gives me little gamma k. Okay. So only the values of this function at those points will determine that quantity, whereas this whole function gives me f tilde. Or maybe I should call it phi to be consistent with what I have used later. So if you look at this gamma of h, k, whatever, the formula for that would be something like this, right? This is also my gamma h. H or k, sorry. As long as we are working with integers, they're the same. For gamma h, when I look at f of omega, I don't need this anymore. If it survives, it's okay. If it doesn't, I will sacrifice it. So you'll have so we are supposing all sorts of weak dependence conditions, which means things are summable, this is integrable, that is integrable. You can write this sum. I used k already. It's possible. If you have integrability, this is an interval where this function cosine k of omega by periodicity will essentially get to something like right? And again, periodicity can also define it that way. So you know what f of omega is in terms of phi of omega. It is this folded spectral density in the continuous case. That's what gives us that. So I cannot learn about all of phi, but I can learn only about f, which kind of combines the values. Right? All right. So if we, to begin with, suppose that we have only a discrete process, it is f or little gamma, that's all we can recover. And if it is on the continuous scale, then phi and capital gamma, those are the things that we can recover, hopefully. Any questions? All right. So we already know how to, again, estimate the spectral density f or this function little gamma if we have a time series where the observations are taken at each of these integer points 1 through n, for example, right? There are standard estimation procedures available. But now we want to look at unevenly spaced data in the discrete setup. So framework 1 refers to the discrete setup. You can think of many scenarios, but this is one scenario for which there is some theory that has been worked out when you are trying to estimate the function f or the function little gamma. And in time series literature, it is called amplitude modulated series that is derived from a parent series. So to begin with, we have xt, a discrete time parameter process. We'll suppose that it has mean 0. It is second order stationary. I write ACVF for auto-covariance function. Okay, ACF sometimes is autocorrelation or covariance. For us, this is only the covariance function, and the spectral density f. This is again following the same notation. And the setup that we have here is more like we have observations that are missing at a periodic, in a periodic pattern. So for a given length alpha, that is a positive integer, capital N is the collection of all positive integers. So starting from time point 1 up to alpha, you observe x1 through x alpha. Then for another stretch of length beta, so x of alpha plus 1, alpha plus 2, up to x of alpha plus beta, we don't observe the xt series. Then again, we are going to observe xt for length alpha, and then we don't have values for the next beta t's. So what we have essentially a process zt, which is obtained from xt by multiplying it with a function gt, and this gt function is equal to 1. It's constant, it's periodic, and it is constant from 1 to alpha, and it is 0 between alpha plus 1 to alpha plus beta, and then you extend it periodically. So when you look at the observations that you get, again, these are the values coming from the original series, then zeros, etc. This is one possible pattern. If you are looking at some of the observations taken on stars, day and night, that's what this is. You do not see or get observations during daytime. So we are just setting it to 0. then again you see something.
But we can set the values anything, right? In any fixed value.
Yes. So, I mean, this is a particular setup for which I have some formulas. This GT can be more general. It doesn't have to follow the pattern alpha, beta, alpha, beta. If there are arbitrary points, even if you are just looking at the observations coming during the night, you do not always get observations always, cloud covers or other disturbances. So you are going to put the corresponding GTs equal to 0. Okay? So those are covered under this framework. But what I'm going to present is only this periodic structure.
Zeros, that means 0 is a value, but those observations are not available.
That is correct.
So these are different kind of things. Yeah.
Yes, so this is sensible because we are supposing that we have taken care of the mean structure. Okay. Otherwise, for arbitrary values, if you set it equal to 0, it's not a good idea. So it's a de-trended series. How you have done it, that's a different issue. Or how you can do it, that's a different issue. But if you have done that and you're trying to learn about the function little f or gamma h, setting them equal to 0 is probably not a bad idea. Questions?
Does it offer anything as opposed to just omitting those?
Pardon me?
Is it so the zeros? They kind of just denote that here's a value that should have been there. It's like a placeholder almost, instead of just omitting them and just having one.
Squishing them. Squishing them essentially destroys
the fact that but having the zeros there accounts for the fact that there should be
something, and we don't know what that thing is. But we also suppose that there is a structure which guarantees stationarity.
Yeah.
So zeros are placeholders.
Yeah. Okay.
In this case, it is sensible because the mean is 0. If you have some other mean, then setting them equal to 0 is not a good idea. Yeah. So if I write AM, it's amplitude modulated version. So when you look at your observations, either for the periods where you do not have any observation, you can say they are missing, R will tell you NA, but if you suppose that you're replacing them with zeros, then you have this ZT process. For the ZT process, when you look at covariance structure, its covariance structure is not going to guarantee stationarity anymore. So when you look at the covariance between ZT and Z of t plus h, you have this modulating function g at time point t and at time point t plus h. And so this is not only going to depend on the difference between the two. That makes it non-stationary. But that is all that we have. We have, whether you call them zeros in the missing range or something else, it is only the values of xt that you have over intervals of length alpha that are repeated periodically. From that, can you estimate the function little gamma? If you can estimate that, there is a way to estimate f, hopefully, right? So if you have to guess, what would it be? How you do it, if you can do it, that's a different issue. If you cannot do it, of course, then there's an open problem. That's great. You have to think of some of the implications of this particular structure. So when you are getting observations over a much bigger chunk of time, missing only few, that way, I think the level of difficulty of the problem is much less. And if it is really very, very small, you don't really care. You have enough pairwise differences within these big blocks that you can combine to learn about gamma. So when alpha is much larger than beta, it should be possible The question is, to what extent can you relax that restriction? So it is possible, there is a theory, and this is something that was looked at in the 1960s. The results that I am presenting here, they are due to Emmanuel Perzen. This is his 63 paper. In any case, so the observation that allows us to come up with an estimate of gamma h is the following. When you look at the limit of these averaged covariances at fixed lag h, so t is going from 1 to n minus h. Z of t and z of t plus h, as we have seen, they do depend on this function g. But this limit essentially multiplies gamma of h with a factor, rh. It does not depend on each and every value of the function g. Okay? And the multiplier, you can show that this rh exists for the function g that I have defined. And so you would know rh, this would be a function of alpha and beta. So this is a constant multiplier. If you can estimate this quantity, you are in business. And so essentially you are removing this, you are looking at all the averages of the product of z of t and z of t plus h. Each of them is coming close to gamma h times that g of t times g of t plus h, and this averaging factor essentially is approximately equal to rh. You divide by that. So this would be the candidate estimator for us. But you can do so only when this constant is non-zero. RH is again some kind of generalized autocorrelation.
RH is 0. It depends on the size of alpha and beta. I guess. That's like the
Exactly.
analysis.
Yes. So in the case when R of h is non-zero, this is something that you can do.
And RH always exists?
For that function, yes, it does. And if you look here, you can allow GT to be something other than this alpha and beta structure. In that case, you have to verify that RH exists. There is not guaranteed. All right. How does it look? So there is an expression available. If alpha is less than equal to beta, you're looking at the positive part of alpha minus h as long as h is less than equal to beta. And then it switches, it is h minus beta when h is between beta plus 1 up to alpha plus beta. When alpha is bigger than beta, this factor is the same, but here it's kind of constant between beta and alpha. The difference between alpha minus beta divided by alpha plus beta, and this part is again the same, right? So in this case, R of h is never 0. In that case, R of h can be equal to 0. So whenever this h is bigger than alpha, but it is still not up to beta, for all of those values, this is 0. Right? So when you are looking at this formula, if alpha is bigger than beta, there is nothing to worry about. So you can estimate gamma. And that means you are only going to be able to use these formulas to estimate gamma of h when you are getting more observations compared to the amount of observations that are missing. And so for the rest of this presentation, alpha is bigger than beta. So we can always find an RH that is non-zero. questions.
Is there like a continuous like analog of this? So it's like, so this is where you have like discrete points where you should have observed something. But is there something like, is there like an analogous notion of what alpha is and what beta is? If your time points are like a continuous. Does that make sense?
No, it does make sense.
It sounds like it would be really hard to make that definition rigorous, maybe.
Sums will be replaced by integrals. I do not think anybody has looked into it, because when we go to this continuous sort of underlying process structure, then the formulation of missingness or unevenly spaced data locations, that is done differently. But if you have a structure like this, it should be possible to come up with an analog of these. It should be. As I said, this is just an average, right? So take the integral from t equal to 0 to some n, divide by n. It should converge to something in the continuous scale. And it should not be that difficult. It's just that nobody has looked into. At least I do not know if anybody has done it. Yeah, yeah, yeah. All right. So if you come up with an estimator, you have to prove its properties, and these properties are proved only for the Gaussian case. As I said, this is a 63 paper. People were trying to understand what sort of definitions of the spectral density, what sort of estimators are relevant, but in any case, this condition is very, very weak. You're supposing that when you're looking at the sum of squares of gamma h goes from 1 to n, divide that with n. As long as that limit is 0, the estimator that we have seen in the last page converges to the true gamma h, that is for the underlying x process. So this is mean square error consistent. And it's easy to show that if gamma h barely goes to 0, that's good enough. You don't need anything more, right? So very weak conditions. You can also guess why you have this gamma h squared coming from that. Because it's a Gaussian process. Fourth order cumulants are 0. And when you're looking at expectation of xt square, or covariance between xt square and x of t plus h square, it would be gamma h squared. So the Gaussianity is used pretty heavily, but the conditions are very, very weak. This is true whenever gamma h goes to 0. Alternatives to this Gaussian assumption would be to impose some kind of mixing conditions, and you will need at least 4 moments. It is 2 raised to the power 2 plus some delta. All right, now if you can estimate these gamma h's for a large number of h's, there is a way to come up with an estimate of the spectral density f. F is again defined by that formula. You truncate the series at some finite level, and then estimate each of those gamma h's with gamma hat h, and that should be a sensible way to estimate the spectral density. And Parzen is one of the contributors, but there is Rosenblatt. A lot of people who have looked at properties of the spectral density estimate. Essentially what you need to use weights. This b is something that is going to infinity, but not as fast as n. I think I didn't say this right. N by b should be going to 0. I'm sorry. N by b should be going to infinity. B by n should go to 0. That's all I meant to say here. Okay. These conditions are not stated right. And the weight function k has to be such that when you approach 0, k of u should converge to converge to 1 at a rate, preferably. You can always take k of u identical equal to 1. That is the naive estimator. It does not always give you a non-negative spectral density estimate. So typically, the rate of decay here will use an R that is bigger than equal to 1, either 1 or 2. So this would be more like mimicking the standard spectral density estimation, where these estimators are constructed with whatever modifications we have seen. And there is an exact expression for the limit of this quantity. Okay. Again, we are looking at the short range dependent case. The variance will decay at the right rate. It is n times the bandwidth. It goes to the right quantity, or it's similar to what happens in the case you don't have any missing observations. It's f of omega squared. But then there is second factor. And that factor, it depends on alpha and beta. I'm just looking at the case when p is odd. There is a formula for the case when p is even. It's a little more complicated. But this already looks complicated to me in any case. So what it has contributions from the function g that is giving these coefficients a of ts. It is also looking at the spectral density, underlying spectral density at omega, plus some Fourier frequency lambda t, where the frequencies here are coming from twice by t divided by p. P is alpha plus beta. So it's a periodic function. You're going to look at these p many Fourier frequencies. Product of these, they are going to contribute to the scaled variance. So you have mean square consistency of your spectral density estimate. It is going to decay at the rate 1 over n over b, but the constant that you get is much larger than what you get when you have no missing observation. This is the contribution coming from having no observations in those periodic intervals of length beta. So in the case of no missing observation, this is the formula that you get. You can compare the corresponding variances. The variances admit an upper bound of this form. And so having alpha and beta equal, that's not a good idea. So day and night, that's not going to let us come up with a very good estimate here. You need alpha to be much bigger than beta in order for these to achieve the same level of accuracy. And you can look at other functions gt that will suit your the application that you are interested in. Something similar can be worked out. There are expressions for these that are given in this paper. This appeared in Shankha. It's a 63 paper. Digging out may not be so easy, but that's where it is. Any questions? All right. So we go to part 2 in some sense. So now we are looking at the line down there which says what? The underlying process is defined on the continuum. And we are after this full function phi of omega, that is the spectral density, where omega runs over all of the real line. It also looks at gamma of t. T also ranges from minus infinity to plus infinity. And we should be able to come up with estimates of phi and gamma when we have unevenly spaced observations. Okay. But in this situation, our goal or objective is much more difficult. And the type of models or formulations that you'd use for unevenly spaced time series data, that is slightly different. So this is again coming from some Google search. I was looking for examples of unevenly spaced time series in astronomy. So it doesn't say much about what these values are. Timestamp, something else. But it has more or less the features of unevenly spaced data that you'd like to see. So these are values that are recorded at arbitrary times during days. On some days there are no observations, and on some days there are multiple observations at different time points. Okay? So I cannot just say I have something here, nothing there, something here, nothing there. Periodicity does not help here. But again, that is an open question. The question that you asked, one has to see if that makes any sense in this context. So I'll note two things here. When you look at the concentration of the points, the locations at which you have an observation, those concentrations is not uniform. Some places will have many more observations, other places will probably have nothing, or something sparse. And when you look at the length on the time scale, length of the time interval on which you are taking your observations, the length of that and the number of data locations or values at which you have timestamps at which you have taken the observations, that number, they don't have to be comparable, right? So you have non-uniform distribution of locations, and when you look at the sample size and the length of the time interval, they may not be comparable. So again, we are going back to the same notation, T1 through Tn, which in the next slide we will become S1 through Sn, but we still have those n time points in some interval 0 to lambda. So lambda here is the domain of observations, like from January up to December in that last example. And n would be the number of data locations at which you have an observations. So for the example that I have shown, and it's typical of many other data sets, these locations will not fall in a regular grid where you can specify the minimum distance and hold that fixed. Okay? So they can come arbitrarily close, and the distribution is not always uniform. So when you have situations like this, both of those factors will have some impact on any estimation procedure that you consider, including looking at the periodogram, trying to identify the peaks. It's not guaranteed. But first, we have to come up with a framework that would allow us to capture these two features. One is that non-uniform distribution of the data locations. You have concentrations in some parts and sparsity in other parts. And also the fact that the sample size and the length of the intervals, they are not necessarily comparable. Okay? You have to somehow separate those two out. Whenever you're looking at any of these, what should I say, the discrete time parameter processes, whenever you fix alpha and beta, the number of observations that you're getting is something like n, the length of interval, times alpha by alpha plus beta. It's of the same order as the length. And that is not necessarily true here. You have to separate those two factors out. So one way to do so is to use a stochastic sampling design. And typically when you look at engineering applications, people would just come up with some sort of a Poisson process that they fit to the time locations. Look at the intensity function that describes how you are going to determine the sampling locations. And since you have non-uniformity, that means you have to have non-homogeneous Poisson process. As I said, for some reason, we want to distinguish between the case of deterministic time points and the stochastic sampling design. So instead of writing T1 through Tn, I'm just going to use S1 through Sn. It's just change in notation. So whenever you see S, it should remind of this stochastic nature. But what are the components here? So the way we are going to model this or come up with a framework that kind of captures those two features is that we have a collection of IID random variables. So I said I will change from F to phi. This is the reason. I need two densities. Okay. One is trying to tell us something about the distribution of the time points. That density is F. It is the spatial or the density that gives me, that determines the sampling design or gives me the locations of those points or the concentrations. So U case they are IID with some distribution or PDF F over 0 to 1. So UI is a number between 0 and 1 with different concentrations. And when I'm looking at S1 through Sn, these are taken over a time interval from 0 to lambda. Okay, so essentially these are going to be these realizations of these UKs are scaled by lambda to give us the locations S1 through Sn. Why does one care? At this stage, it is making things more complicated at the expense of making some of the final expressions simpler. It is possible you can consider the interval 0 to lambda in random variables taking values according to some density on 0 to lambda, and that would give you S1 through Sn. That is fine. All I am saying is that if I have this scaling property, I'll get final expressions that will not depend on these individual S1 through Sn. It will depend on their distribution only through the function f. That's the only reason. Okay? So it's a matter of choice whether you make life complicated at this stage to simplify something that will come later on, or you work with these locations S1 through Sn with some arbitrary distribution over 0 to lambda. That is also possible. Okay, so non-uniformity is essentially captured by this function f, right? It doesn't have to be uniform over 0 to 1. And when you look at the relative sizes of the sample size and the length of the interval, they can be very different because you can generate as many of these random variables as you want corresponding to the locations, data locations. So these two factors, they can be separated out. You have non-uniformity, you have relative differential growth rates of sample size and the length of the interval.
Just one minute, last
Yeah,
line.
sure.
So again, the last line saying that you are having intuitively like one observation every lambda time, right? This lambda times UI is the spacing of the data generating process.
That gives you the location. Spacing should be you look at the order statistic I plus 1 and I minus 1. That's what is going to give you the spacings. So essentially you are throwing in points according to this distribution f. If you look at the histogram where f has mode, for example, there will be many such observations. And where f has a very light sort of tail, there are very few observations.
Right.
Yeah, okay. Any other question? Okay. All right, so I'm setting up notations again. So our data would be, again, observing the z process. The underlying process would be continuous parameter. I denote that by z of s. Data will consist of the values of this process at locations S1 through Sn, and the SIs are generated by the mechanism that I have said before. The underlying process Z is second order stationary, zero mean, or it doesn't have to be zero mean. You can allow at this stage non-zero mean, but eventually it will be zero mean. And we would also suppose that it has enough moment, so we don't have to worry about using moment bounds. And also weak dependence. When things are far apart, they are kind of independent. So this is the expectation is missing here, sorry. So the simplest parameter would be the mean of this Z process, which I denote by mu, and you would estimate it with the average of all of these Z of SIs, the data values. Okay. Now one has to be careful about properties of Z bar. Statisticians always do averagings. Most of the time they are lucky, it works, but sometimes it will not work. All right? And it does depend on some of these structural intricacies. So we are going to suppose that the length of the interval that becomes a function of the sample size. So if you are looking at large sample properties, or what happens in the limit is given by the number of points, data points. N is the variable that determines this asymptotics. So one case is when lambda n is not going to infinity, it is bounded. Okay, so you have a time interval 0 to lambda n, or lambda for example, and you are taking observations S1 through Sn, n is going to infinity, which means that finite interval is getting filled in very, very densely. That is case 1. And case 2 is saying that I would allow the length of the interval to increase. So if you are taking observations over time, and as time goes by, you collect more and more observations there. But again, the relative sizes of these two would be important. D is carried over from the special case. So D is 1 for us. You are going to look at the relative density of the points in the interval 0 to lambda. And so if there are n such points, and the length of the interval is lambda, on the average, this is what you expect in an interval of unit length, right? The whole thing is lambda, there are n, divide n by lambda. That's the density, average density on unit intervals. So if that goes to a constant bigger than 0, less than infinity, this is what in spatial statistics people call PID, pure increasing domain asymptotic structure. And in the case where you have the average number of observations per unit interval going to infinity, so you're taking many more observations per unit interval than what you do in case 2.1, then you have mixed increasing domain asymptotic structure. It is mixed because this is called infill. When you are looking at a bounded interval and you fill that in with many, many observations, n is going to infinity, you're filling in the bounded interval. So that is the infill structure. And if you allow lambda n go to infinity, you're increasing the domain of observation. So these two are the most common types of asymptotic structures people use. And sometimes these are driven by what your objectives are, what you want to do. With infill asymptotics, if you are trying to estimate characteristics of the underlying process, like these functions, the autocovariance function, or even sample mean, it may not give you the right answer. On the other hand, when you are trying to estimate a continuous function phi of omega, where omega ranges over all of the real line, you need observations that are coming very close. So both of these characteristics are important, which is leading to this one. It is mixed increasing domain. In any case, so what is important from here is that depending on whether we are in case 1 or case 2, what we should expect about properties of estimators like Z bar, that will change. And that will change very drastically. And the case that I have left out is when C star is equal to 0. What does that mean? That means, again, this is the number of observations per unit time interval. And that is almost like 0. To get 2 of these observations, you have to travel very far in the time interval. So the observations are very sparse. Naturally, that corresponds to approximate independence. And then we know what to do. That's not a challenge. OK. So case 1, when you are looking at this infill case, we have a bounded interval. We are taking many, many observations. In that case, just suppose lambda n is lambda naught. Nobody cares. In that case, Zn bar will converge to not a constant, but to a random limit. So you do not have consistency. You have n observations. You have averaged them with the hope that that will reduce the variability. But this really does not kill the variability. It has a random limit. So if you have enough moments, you look at the variance of this, that will go to the variance of that, and that is non-zero. So averaging does not help here. And part of the reason is when you look at a bounded interval, I have put some smoothness condition here. These are mean square continuous processes, which means essentially the paths are continuous for most of the sample space. And so if you know what is happening at a time point and you come very close, that's what is happening when you are infilling 0 to 1, for example. There is not enough information. You are not learning about the, I should say, distributional characteristics of the Z process. So that you cannot really do anything about. So there is not enough information, even if you have taken as many observations as you want, as long as your interval of observation is bounded. So that's what kills this averaging process. It does not give you the answer that you want. So this is not consistent. So the references, if you're interested in infill asymptotics, Michael Stein, he is associated with this program also. So he has a series of papers, and he also has a book. Look at that. That tells much more about implications of this infill asymptotics. So now we can look at leave out case 1. Case 1 is hopeless. If we are trying to estimate phi or capital gamma, that structure, case 1, that is not going to work. So what we can do is to look at lambda n going to infinity, that is the increasing domain asymptotics. In this case, you get a central limit theorem with some modifications. The multiplier here is not dependent on how many observations you have taken. It is dependent on the length of this time interval. So if you have 2 years worth of observation type on a satellite, and then you think you are going to take observations every 2 seconds, that may not be very useful. As useful as if you could extend that observation time further in this framework. So it is the length of observation interval, that's what, square root of that, that's what gives you the accuracy of Zn bar when you're estimating mu. Yes.
When n by lambda n belongs to goes to C star, which belongs to 0 to infinity open,
Yes.
then we can replace lambda n by n, right?
That is correct. Yes. So that will have some impact here. So in that case, that is the pure increasing domain structure according to the terminology. In that case, lambda n and n, they are comparable, so you still get root n consistency. But I'm talking about when you are trying to fill in with more density, it's not going to help you much. The only thing is that this part that drops out. So the asymptotic variance becomes a little smaller if you have many more observations, but rate-wise it does not help. You get, so there is more like an asymptote. You do not go beyond that level. It's the length of the interval of observation. That's what determines the rate of convergence. And when you look at the form of this asymptotic variance, it has the spectral density at 0, just like when you're looking at the discrete parameter case, you're looking at xn bar, the limit distribution. When you again subtract the mean multiplied by square root of n, that will go to normal 0 twice pi f of 0. Something similar happens here too. It is twice pi phi of 0. And this is the sampling density, the non-uniform distribution of the points. Somehow you are able to again capture effects of all of those non-uniformity with this function f. So that's the simplification I was talking about. Otherwise, you have to carry around some arbitrary functions of S1 through Sn, how they are distributed. And this gamma 0, of course, is the variance of the z process. When c star is infinity, that drops out, you get some reduction. I think I just talked about this one. This is the folded density. That's what happens in the regular grid case. And the implications are confidence intervals, do not expect those to shrink at rate 1 over square root of the sample size. It is 1 over square root of lambda n. If you are trying to set confidence interval, you still have to come up with estimates of this. And that makes any sort of task, if you are trying to do testing about mu or those gammas or phis, that's much harder, because now you have to contend with not only this underlying covariance structure, but also with this and so on. So there are ways, if we have time and enough energy, we'll go through it. If not, you know what to look for. I think this is the reference. There is a version of log bootstrap. So what is the time now?
Almost 5:43.
5:45. So we have covered more than 1 hour. Good place to take a break, or?
We should certainly take a break,
Okay.
and then we can discuss or we can continue whatever.
So I'm only on page 30. And if you could see the whole thing, I have 101. So yeah, I think we'll take a break now. Thank you. So most of what I'm going to say will be under case 2, where we have an increasing domain of observation. So lambda n is going to go to infinity, but this c star can either be finite or infinite. All right, so about the mean, we have some results. Now, if we want to consider estimation of the second order structures, oftentimes you are going to work with the periodogram or the discrete Fourier transform. So these SJs, these are essentially unevenly spaced. We are going to follow or mimic the definition that appears in the regularly spaced data locations case. So in that case, S of j would be just j, right? And you look at the product between the value of this process at time point j or sj, e to the power I omega transpose is not there. It was, as I said, for the spatial case. So in the one-dimensional case, it is omega times sj. But the scaling here you can again get the sense of why this is the right scaling that will give you a variance for the real and the imaginary parts of dn omega that is not vanishing or blowing up is the following. What you're looking at, if you just put omega equal to 0, this is z bar. And when you looked at the central limit theorem, that said you had to multiply this minus the expectation by square root of lambda. So that's what gives you the right sort of scaling when you define the DFT. That kind of balances the variances of the real and the imaginary parts. And so if you look at the real part, that would be the cosine transform. I denote that by Cn of omega. And the sine transform is Sn of omega. All right, so we are now building machineries that would be useful if we are going to make use of the DFT. In the regularly spaced case, the DFT of a second order stationary process with some structure that has two important properties. One is that if you are looking at the periodogram that is based on the DFT at any Fourier frequency, that essentially has enough information about the spectral density at that frequency, right? The second one is that when you look at the corresponding sine and cosine transforms, they are going to be asymptotically independent. So that is the case when you have this regularity of the sampling points. The theorem that we have here that says something similar is true. Okay, so the sine and cosine transforms, if you fix a particular sequence of frequencies, and I'm not necessarily looking at Fourier frequency, it is not of the form twice pi j by n. It doesn't make sense in the case when you have a process on the continuum. Okay, twice pi does not mean anything. In the case when you have discrete parameter, the spectral density is from minus pi to plus pi. So there twice pi makes sense. But in any case, so these are arbitrary frequencies converging to a non-zero real number. And they should not add up to 0 or be the negative or be equal actually. So in that case, when you look at the limiting variance covariance matrix, for each of these frequency sequences, the pair Cn, Sn, they will have a distribution with the same variance. So A1 corresponds to omega 1, A2 will correspond to omega 2, and AR corresponding to the frequency omega Rn. Which means essentially these two, their variabilities are comparable. They are going to be uncorrelated as you go from one frequency to the other. The only condition is that one cannot be the negative of the other, or they are equal. Okay? If you are going to distinct frequencies, you are fine. As long as these conditions don't fail. The other thing that you have to note here is something similar to what happened when you looked at the distribution of Z bar. It does have information about the spectral density at the limiting frequency omega j, but there is a disturbance. And this disturbance does not go away even when you are working with the mixed increasing domain case where C star is infinity. So in the limit, of course, you don't get that. But in finite sample, you are never at C star equal to infinity. You are looking at the length of the interval lambda n, that is a finite quantity, and number of points n, their ratio that can be very, very large, but still something that will have an effect on the actual variances of these two quantities. So if you are trying to estimate, for example, phi of omega j, these are multipliers, constant multipliers, kind of corrupted by a term that's more like the bias. And somehow you have to correct for it. And that is the price you pay just going from this regularly spaced data points to having this irregular spacing. Unevenly spaced data locations, they contribute this term as well as this factor. And you have to take care of both as you are trying to devise, for example, an estimate of phi of omega. So irregular spacing still has the asymptotic independence property, but with some complications. You need some adjustments for the first term. And remember that you're not trying to estimate f of omega, where omega lies between minus pi to plus pi. Your goal is now to estimate phi, which is for omega lying in the real line. All right, so the standard quantity that people do use to estimate the spectral density in the regularly spaced case would be the periodogram, which is again the modulus of the DFT squared. And this is not a good quantity to use in the unevenly spaced case. What you should be using is In of omega, but now you're adjusting for the first term that appears in there. Cn star is not something that you always know, because when you are using a particular data set, nobody gives you the limit. It's only 1n, 1 lambda n. So you have to substitute in place of C star the ratio of those two numbers, whatever that is. And this should be capital gamma hat n0, but they're the same at integer points, so I think I'm okay. This is an estimate of the variance of the process. Okay. All right. So your goal can be twofold. You can try to estimate the spectral density. Here, estimation of the covariance function is also something of interest. And like Eric was saying, if you are looking at a lag h is now a real number. You have n data points observed at S1 through Sn. So when you look at the pairwise distances, it is only Si minus Sj. And there are n choose 2 such non-zero differences. So how do you come up with an estimate of the covariance function? And that has to be over the whole real line. I have put two references here. And they do give you some methods of estimating the covariance function. But before I get into that, what is the rate that you'd expect for an estimate of the covariance function to satisfy if you're in a setup like this? Let's again forget about the mixed increasing domain asymptotic structure. It's just the PID, which means the length of the interval of observation and number of points, they're comparable order. So I'll rephrase the question. Is it possible that you can estimate rho of h, or I'm sorry, gamma of h, gamma of t at the rate 1 over square root of n? You have n observations. You're trying to estimate a function on the continuum. Lambda and n, they are comparable. When you look at the literature on non-parametric functional estimation, you're trying to estimate the, the regression function, density function. Usually you cannot achieve root n consistency. That's because of the bias. And the bias comes from the fact that you have too many values to estimate the number of data points in a local neighborhood of whatever functional you are interested in would be of smaller order than the full sample size, as long as you are trying to keep it unbiased, or at least asymptotically unbiased. That kills the rate, right? You use a bandwidth, it's n times h, that's the local order of the points corresponding to a particular value of the functional. And h has to go to 0, otherwise the bias is non-trivial. But something strange happens here. So we'll proceed as if we are again trying to estimate this function gamma using this kernel smoothing. Okay. So gamma hat of h would be, look at all pairwise differences. S of ij is si minus sj, all right? And then see which one of these they come close to the lag that you're interested in, the particular h. These are weights. Weights are coming from some kernel function. And b is the bandwidth here. That kind of tells you to what distance from h you are going to allow these zij's to come in. And zij's are again the cross product of the centered z values. So this is a sensible estimator, and from what we know, if these si's were exactly equal to I, this is going to grow like, the variance of this is going to decay like 1 over n times h, or n times b. b is going to 0 here. Okay? So you cannot really get root n consistency. That's one problem. The other problem, you're trying to estimate the covariance function, the autocovariance function. That should have this non-negative definiteness property, right? And when you do this local smoothing, there is nothing that guarantees that this as a function of h will have non-negative definiteness. So if you are trying to do predictions and make use of these estimated values, you are in trouble. Okay. So the trick here is the following. It's not easy to ensure that an estimated function is non-negative definite. But if you look at the corresponding estimate of the spectral density coming from this estimate by this inversion formula, whatever I have written there, you are essentially replacing the integral from minus infinity to plus infinity to a finite interval from minus cn to plus cn. Let cn go to infinity at certain rate. Then this would be an estimate of the spectral density. And since to begin with I do not have a non-negative definite function, my spectral density is never guaranteed to be non-negative, right? There's some theorem by people long back. So what you have to do is not use this as your estimate of the spectral density, but look at the non-negative part. That is something that is easy to ensure, right? And then invert it back. So look at the inversion of this non-negative part of this estimated spectral density. You start in the time domain, go to the frequency domain, do this thresholding, get back to the time domain. Okay? So I'm moving things around. But this estimator becomes non-negative because of the fact that this is already non-negative. All right, so this is a modification anybody should have thought of, right? And people, I think, are aware of it now. The question is, if you are starting here, going back there, coming back with some operations in the intermediate step, what happens to the properties of this estimator? How much of it is retained? First of all, I am saying this integral is from minus infinity to plus infinity. Is this something sensible?
Not in practice.
So we were careful here. We are not careful there. But if you did this, that somehow induces enough regularity in this phi hat plus that will ensure that this is well defined. All you need is Parseval's identity.
What identity?
Parseval's identity. So this minus gamma h, you look at phi tilde minus phi. So the L2 norm of that would be the L2 norm of phi tilde minus phi. L2 norm of phi tilde minus phi, phi is non-negative, would be less than or equal to the L2 norm of phi hat minus phi. L2 norm of phi hat minus phi would be determined by gamma hat h restricted to this set, that is finite. So this would be well defined, but with whatever tricks. And this is non-negative definite. And this is the property that was proved by Peter Hall and his co-authors. What it says is that when you look at this gamma hat of h minus gamma h, you can let a go to infinity too at a certain rate, but this is for any fixed a. When you look at the L2 distance integrated over plus minus a, you are multiplying this with lambda n. And that has a limit. It goes to a Gaussian process. It's stabilized. So the rate of approximation of this to that is square root of n, square root of lambda n. Okay? So whatever we do just by taking the first step, that is this local estimation of the covariance function, that is very, very inefficient. That will not give you this root n rate of consistency. That will not guarantee the non-negative definiteness of your covariance function. But again, going to the frequency domain and taking care of those negative values and coming back gives you an estimator. Proof is not easy, of course. I mean, there are lots of intermediate steps. You have to analyze each part and see however much error you are making in each step. But anyway, Peter Hall can do this. So that's the final result. And so if you are trying to estimate the autocovariance function on the continuum, this is what you should be doing. This is the right way to do it.
Is this published and well used, or is this something you're proposing here?
No, this is published, 94.
And that's Peter Hall.
That's Peter Hall. And somebody said there is only one Peter Hall, so only he can do it. I cannot. All right, so yeah.
So if you have, instead of a general time series, if you have a parameterized time series that induces a parameterized gamma h,
Yes.
then is there any way? I mean, then you'd expect that you can have root n consistency, right?
Yes, if your parameterization is smooth, that is possible. Yes, so Whittle estimation will do that.
What is
Whittle estimation? Yes. Again, I cannot say use, may use Whittle likelihood when gamma of h is equal to some. So if you have finite dimensional parameters, that's the way people do. That attains root n consistency. There is a paper in 2010 by Matsuda and Yazima in GRSSB. That reference appears here too, if we get to go all the way. But I was stopping to ask how much energy and time we have left.
6:15.
45 minutes? Go ahead.
Should we?
We're still here.
I know, but I do not want to overdo. So if you at any time point say stop, I'll stop. And if not, then I'll continue. All right. So this is moving on to something else. It's a part of a talk that I think I gave in the opening workshop, but I did not get to cover this empirical likelihood, for example. I could not even go through the first part of this stochastic sampling design that threw people off. But in any case, so hopefully we'll do some of this. All right. So when you're trying to do inference, you need ways to calibrate either your test or your confidence intervals. For that, there are standard methods. If you have a limit theorem, that's what you'd use. And we do have central limit theorems now, which will allow you to derive, again, limit distributions of MLEs or related estimators that are asymptotically linear. You can also look at bootstrap methods, particularly if you're trying to estimate the variance. The variance has now different components coming from your non-uniformity of the sampling points, as well as the underlying covariance structure of the time series on the continuum. So bootstrapping is possible, and there is something called empirical likelihood. One thing that people often will not tell you, when you're doing the bootstrap, if your goal is to estimate the standard errors, great, you can do it in many cases. If you are trying to improve the coverage accuracy, for one-sided confidence intervals, the bootstrap is good in regular models. You get something better than using the limit distribution. But if you're going to the two-sided case, that's what people use most often. Bootstrap confidence intervals are just as accurate as those based on normal approximation. So you do not really gain much. So going through all of those resampling, computing your estimator essentially leads you to something which you can do just by looking up on the table, right? In most cases. So in that case, what you should be using, there are fixes, of course. I mean, there are specifically targeted bootstrap confidence intervals that will improve in the two-sided case the coverage accuracy. That is done. But if you are just using percentile t without any modification, it's not going to give you any more, again, level of accuracy that is better than what is based on the normal approximation. In that case, what you might want to do is to also look at empirical likelihood. That has some advantages, particularly in situations like this where estimation of the asymptotic variance is not, it might be fun, but not very easy. Anyway, so these are two classes of methods. I am going to probably look at some of the block bootstrap methods. And what does a block bootstrap method do? Like any bootstrap, if you have a time series, your goal here is to reconstruct a replica of that. And blocking is important because that kind of preserves the local interaction structure. So you're going to look at blocks of suitable lengths, resample blocks of values, put them together. That part is not very good. But then what you have generated is a version of the original time series with some distortions at the joint points. And
Jumble up blocks basically is the bootstrapping.
say that again?
So to like actually bootstrap, you're kind of just like sampling from those blocks, just kind of moving them around sort of.
Yes, so it is possible the first block itself appears 3 times, and first one is followed by the last one. All of those variations.
You lose the order of the blocks when you start sampling.
Yes. But what is important is that is the local interaction patterns that you're preserving within blocks. Beyond that, if you're looking at observation from one block and another observation from a different block, you cannot say anything. They're independent. So it works in problems where essentially you have very weak dependence going further out. And it's important to keep track of what happens in essentially in the immediate neighborhood. Then it's okay. All right, so this is again something that I picked up from the internet. All right, so this describes how you do the bootstrap. This is a little more general than what I was going to say, but let me give it a shot. So I have a time series of length n. I select a block length L. So my first block is going to be going from 1 to L. So Z1 through ZL, or in this case it's regularly spaced, so X1 through XL. Then you shift the starting point by some distance m, and the next block will start from m. This is the first block. This is going to start from, anyway, I don't know. Can you read those letters, L, M, etc.? Not very clearly. So the simplest version would be you have the series x1 through xn. You pick a block size L. Then you look at the disjoint chunks 1 through L, L plus 1 to 2L, and so on. That is the non-overlapping block bootstrap. That does not allow overlaps of the blocks. The other extreme would be you start from x1 to xl. The next one will start from x2, go up to L plus 1, and so on. That is the maximal overlapping blocks. And this is somewhere in between. Instead of starting from x2, you are now going to start from x of m. M is some number between 1 and L. And so it will allow for some overlap between the first and the next one, and keeps on going. So when m is exactly equal to 1, you are just going to start from x2, go up to L plus 1, and so on. But if you pick an m that is bigger than 1, but still less than L, then there would be overlaps of order L minus m. And that is something that people use to reduce computation. But when you look at theoretical properties, I don't think you gain anything more. So these are the extreme points. Any other m will give you properties where it is somewhat in between. But the idea is again to partition your original time series into smaller subseries of length L, and how you pick the subcollection of blocks that determines different versions of block bootstrap.
And for irregularly spaced, these L's are in clock time, not number of data points.
Okay, so irregular spaced case is very difficult. All right, this is what I'm going to try to explain next.
Okay.
So the construction is, you're right. This construction
This
is
for
when
evenly spaced.
evenly spaced all data points.
Thank you.
Okay. Now you have points essentially distributed non-uniformly over the whole interval 0 to lambda. How are you going to construct your blocks? And if you go by this, here the starting point can be x1, x2, x3, all of those, when you have regular spacing as well as no missing values. You do not have regular spacing. Missing value doesn't make sense. I'm not trying to cover any fixed grid. So once I have this, you're still going to look at part of this interval, 0 to lambda, partition it in some ways. So it's lambda by some number that tells you however many blocks you want. And then you're going to shift those. So 0 to L, 1 to L plus 1, that's a possibility. L would be much smaller than lambda. Okay, so you're going by the length of the series or the length of the observation region, not by S1 through Sn per se, when you're specifying the blocks. And I said there are at least two ways of constructing the blocks. You can, there is no x1, There is no 1, 2, 3, 4. You have S1, S2, Sn, and I did not even say S1 is less than S2 less than Sn. But we can suppose that that's how we have numbered. But then you know the length, that is something of smaller than lambda. You can start at each of these data locations, data sites, shifting that template 0 to L, or I just ignore the positions of S1 through Sn. I pick my grid, integer grid, 1, 2, 3, 4. I'll start my blocks from 1 to L, 2 to L plus 1, etc. These are two different ways of doing it. So this is my template, V0. I am fixing some length L. L was capital L in that picture that I have shown. So this is the length of the subseries for subinterval. So for these are mouthful acronyms. I think I said DSB because I didn't want to say DSSBB. Okay. So DSB and GBB, these are the two things that I'm going to say. Okay, so one extra B. In any case, so when we are looking at DSB, I have this template. I'm going to ship that using the observation locations S1 through Sn. To the extent I can, as long as the shifted intervals still lie within 0 to lambda. So for the last few, you cannot really define your blocks. So starting point here is given by one of these data sites. And the other one is grid based. As I said, I'll take the integer grid. B0 goes from 0 to L, then 1 to, maybe I'm just saying I bigger than equal to 1, in which case it will go from 1 to L plus 1, similarly 2 to L plus 2, and so on. So in one case, the locations of the data points, they are going to dictate where you start your block. In the other case, it is coming from the integer grid Z. And in both cases, you need the observations. So whatever shifting you're doing, that thing has to be contained in 0 to lambda. If you go either to the right or left of this interval, then you do not have observations. You cannot. So there is no point. And once you have defined the respective collections of blocks with whatever translation method that you have, you are going to resample. Again, if there were n observations, n by L is what you are going to look at. You are going to resample those many blocks and try to reconstruct the original series. And if you have Tn, then you are going to put these resampled values in the same functional definition of Tn. The Zi's would be replaced by the resampled values, and that gives me Tn star, the bootstrap value coming from this DSB or the GBB versions of the block bootstrap. Okay, those are again reconstructing the bootstrap versions. All right, so I have a question for you guys. The last line. There is a right way to do it. There is a wrong way to do it, and one of these methods, either DSB or GBB, that fails. So is there some intuition? Yes, go ahead.
I think the grid method makes more sense. Yeah, that's the data.
Yes.
Because it's just historical coincidence that you have incredibly dense at some point. And you don't want your statistical method to base on just this meaningless coverage by the astronomer. But if you do it with a grid, you impose some rational structure.
Some uniformity. Any other variations of that argument or completely different arguments? There are only two possibilities, so he picked one. Anybody for the other one? But it is 100% correct. So great intuition. So it does not make sense to stack up the blocks corresponding to each of these starting points, because where you have huge concentrations of these points, you are repeating the same chunk of your data values many times. And when you have distributions like this is what is going to dominate, because your resampling is based on uniform weight on all the blocks. So this will get represented many more times than some of the other parts, and that is not a good idea. When you have severe non-uniformity, do not go with, again, blocks that are obtained by shifting by these locations. That will skew your final results. So GBB is the right one that one should be using. So for data sites, shifted block bootstrap, if you look at the estimate of the variance, look at the sample mean, for example, and compute the corresponding bootstrap variance, it does not go to where it should go. You can prove that. And for GBB, it also, so that's a paper with Zhu that shows that it does whatever you want the bootstrap to do. It will give you distributional consistency, variance consistency, all of that. So it doesn't matter what sort of effect you have for this spatial sampling density or the underlying covariance function, it will be able to capture all of that. So some sort of uniformity is what gives you a better representation in the bootstrap world than being guided by the starting points. All right. Should we or should we not? I took 15 minutes, right?
Yeah. 30 minutes left.
Are you okay with that? Okay. All right. I'll try to go over this quickly. So what is it that we are trying to do? We want to come up with an analog of likelihood-based inference procedures, but we do not want any parametric models. So when you talk about empirical likelihood, that's the main idea. You don't have to specify Gaussian model, you don't have to specify Poisson binomial, whatever. We don't care for those. Because when you are dealing with complicated time series structures, just having a covariance function that is determined by 2 or 3 parameters that will not capture all the dynamics. It's not possible. So you want to get away from this parametric modeling to the extent you can. And this is a method that allows you to, again, carry out inferences pretty much in the framework of a parametric model, but without the parametric model. So in the classical case, what happens, we have x1 through xn. Those are IID, independent and identically distributed random variables with a common distribution that is coming from this family of distribution, f of theta. Theta is a finite dimensional parameter, oftentimes just the real line. And you set up the likelihood. Essentially, you evaluate the density at the observations and consider this as a function of the parameter theta. And wherever this function, this is your likelihood function, wherever that, well, I am going ahead of myself. So this is the normal PDF. You have observations, you evaluate all of those, multiply them, that will give you the likelihood function. And if you maximize that, that gives you an estimate of the parameter. And some standard result says you have to look at the likelihood ratio statistic, which essentially compares the likelihood function over all possible values of the parameter and also at the hypothesized value theta equal to theta naught. Then under H naught, this is going to converge to a chi-square distribution. So you have a model, you have a criterion function that you optimize that gives you the MLE, for example. And again, you make use of this likelihood function, plug in MLE and also L of theta naught. That ratio is something that you compute, and negative 2 times log of Rn of theta naught will go to chi-square p, which is free of parameters. You use the quantiles of this to come up with a test for this quantity. And there are many optimality results about the likelihood ratio test when you have some regularity conditions. You can also get confidence intervals. Essentially, if this is the likelihood ratio statistic as a function of theta, you look at the set of values for which this exceeds a threshold, and this set of theta values will give you a confidence interval for the unknown parameter. Empirical likelihood define a likelihood without specifying a parametric model. You can do so for certain population parameters. For the case of the mean, the population mean, this is the formulation. You don't have a model, so what you do, essentially you assign weight pi I, it's a probability weight, to the ith observation. And so when you look at the likelihood, the density evaluated at xi, you're essentially multiplying these pi i's, okay? And pi i's are non-negative, they add up to 1. And because you're trying to see how likely it is that the mean has a particular value mu, you look at the mean under this weighted empirical distribution on xi's. That mean should be equal to the hypothesized value. And when this mu is close to the true value, mu naught, this product is going to be taking large values. And as you move away from the true value, there are very few combinations of pi i's that will give you pi I times xi equal to mu, and so this soup will take a small value. And the ratios of the two that will give you the likelihood ratio, the empirical likelihood ratio for a particular value of mu. Theta is mu, so I didn't change anything here. I didn't change anything here from the last time I gave the talk. That's all I meant. Anyway, so when you're looking at the likelihood ratio statistic under this formulation, the max is at pi I equal to 1 over n for all I, which means the ratio of these two, that's what gives you the empirical likelihood ratio. And I mean, you can define many such methods, but the important thing here is that you mimic the property that was shown before in the case of a parametric model. So -2 times log of this empirical likelihood will have a chi-square distribution. Again, it's free of parameters. You did not need a model. All you need is that optimization of discrete weights, product of those. This is what you have to optimize. This is a convex optimization problem. Pi I xi is more like saying if you have observations, you look at their convex combinations, that has to equal the value mu. And so this essentially tells you you can mimic the parametric likelihood inference sort of approach also with empirical likelihood in the case of the mean. But case of the mean is not always general enough. So you have to look at alternatives that are more general. And again, this is an important paper by Chin and Lawless that says if you have a parameter for which you have a moment condition like this, then you can define also empirical likelihood for such thetas. Okay, there are lots of good things said about empirical likelihood. I'll let you read, or maybe not. So one of the major things that you should appreciate here is that we do not have to estimate the variance. So when we are looking at likelihood ratio test, or we are inverting that to get confidence interval, all I have to compute is this function r of theta. If I can evaluate that in a fine enough grid, essentially we will see where it exceeds the corresponding critical values of the limiting chi-square distribution, and that tells us what values of theta will form my confidence interval. So variance estimation is not needed. If you are looking at the standard studentization based or self-normalization based approaches, then you have to estimate this tau. So that's one advantage. The other advantage is you do not need a parametric model. So you'll never be wrong on specifying your model. You don't need that. All right, so what happens in the dependent case? As I said, I have 101 slides. I will not show you all of them. Do not worry. So in the time series case, again, the idea is something similar. You have to work with blocks. So this is the average of the first block, next block, and so on. Blocking is necessary. Again, you have to capture the interactions of neighboring xt's in the time series case. And it's Yuichi Kitamura who did introduce this version of the empirical likelihood for the time series data. I don't think I'm going to show you that picture again. But he did it in the case where m was not necessarily equal to 1. So it was done in the general context. So what are we going to do? If we want the empirical likelihood, I say block empirical likelihood just because we are putting weights not on the individual xi's but on the block averages. So this is the average of the ith block. There is a weight pi I, and there are as many as n minus capital L plus 1 such overlapping blocks if you fix the block length at L. And so it is the product of all these pi i's that is going to define the BEL values at any particular mu. And there is a version of this chi-square limit, but it does require a multiplier. So the multiplier is known. So you should still be able to use, again, the quantiles of chi-square 1 to calibrate confidence intervals for mu naught, right? And this scale adjustment is like 1 over L. L is the block length. So what is going on, when you looked at the empirical likelihood for the IID case, those observations were independent. When you're looking at this maximum overlapping version, any L of them are overlapping. So essentially you have very strong dependence there. And this L factor kind of takes care of that effect of dependence. All right. So that's what happens for the mean. If you're trying to do inference about the covariance parameters, it is more sensible to go into the frequency domain. Do not work with the time domain. The reason is this block size L. It has a lot of implications about the quality of approximation. Okay? And it is not as good as what you'd expect when you have IID observations. So choice of block length, that is still open. And that is not something that you can really structurally remove because you have to capture the variance of x bar in some sense. So time domain approach to empirical likelihood, that has issues. The main issue is the choice of this block size. If you go to the frequency domain, the life is a little easier because, as I said, in the case where you have regularly spaced time series data, the DFTs, those are the main constructs in the frequency domain, they are asymptotically independent. And when that is the case, you don't have to choose any block size. You can put weights on the corresponding DFTs as long as you are sticking to these Fourier frequencies. And they are approximately independent, and most of the results we'll go through. There is a paper by Nordman that says even under long-range dependence, you get sensible answers when you're using the frequency domain empirical likelihood. These are with regularly spaced time series data. If you go to the irregularly spaced case, that is something very recent, but there is an answer that you get. And as I said, it gives valid answer, and this is a situation where it is very important because even for the sample mean, we have seen that the variance is a function of the underlying spectral density. It depends on this spatial sampling density. It depends on the C star, which is the ratio of 0 to lambda n to number of sample points, etc. So, excuse me. So you do not have to estimate any of those. When you are applying the empirical likelihood in the frequency domain, you don't have to worry about choice of block size. You do not have to worry about choosing or estimating the asymptotic variance. All of those are good. So in some sense, that is the method to use, right? It is 6162. I don't think I want to say that anymore. So the paper that I was referring to, Whittle likelihood, you also have a version of that for irregularly spaced data. But it is much more complicated and has essentially all these ingredients that we get with the limit distribution, the variance in the limit distribution. And you can actually come up with ways to construct confidence intervals for theta using either this empirical likelihood or the Whittle likelihood. Whittle likelihood gives you an estimate of theta, but then you have this asymptotic variance. You have to estimate those to get the corresponding thing. So I would suggest when you are in a situation where variance estimation is a complicated thing, and that is the case if you have unevenly spaced time series data, this is a good idea. I'll stop with that. Thank you. Yeah.
Well,
Okay, now I should go back.
we had in the last few weeks some increasingly sophisticated lectures that were more astronomically oriented, and this one's more sophisticated mathematically. So poor Charlie and I, who have a poor background in this, are trying to keep our nose above water. I'm interested, the three younger statisticians in the room, is this very difficult for you, or is this well within your grasp?
It was awesome.
It was awesome. Okay, here we go. Okay. So, by the way, I've heard, Charlie, some of this twice now.
Yeah.
Because I happen to hear some of it in August. And that really helps me. Okay. But I
Yeah.
still don't have a background enough to fully comprehend things. And I'm sure the young statisticians, when you hear astronomers going on and on and on about transits and periostums and the ellipticities, and you probably have a primitive understanding of some of these terms and concepts, and you struggle, but you hear it 2 or 3 times and you pull something together. Right? So this is the challenge of astrostatistics, and I spend much of my time at a simpler level, sort of what I call the Wikipedia level, of trying to help astronomers learn statistics at Wikipedia level, sort of elementary textbook level, and I'm an educator essentially, so I serve as an educator. But here in this room, I have rarely seen, this is a rare occurrence where the cross-disciplinary communication is being attempted at a professional level, and it's hard.
Yeah, it's hard, it's challenging, but I think that's what
But it's very, this is what
the objective,
SETI is
yes,
about.
yes,
It's not just
yes,
an education institution, it's a research institution.
yes. And also I have an excuse. You said mathematics of uneven leaf
Yes.
space. So I can do anything. No pictures. I'm still okay.
But eventually, we would want to try to connect some of this advanced mathematics with what astronomers are doing. They often do things that are sort of vaguely mumbling, maybe right or wrong, okay, but to address their practice. And then to take some of their more important data sets and try to do some of the more correct things, statistically correct things, to show them what this sophisticated, after you've read a Biometrica analysis of statistics and whatever, and you've, how would you guys analyze some of these data sets? And so that is the step we cannot do in a lecture here.
That's true.
But what SAMC as a 9-month research effort can try to do is, I believe two things. One is the critique of astronomers. I don't think this is useless. I think it's important for statisticians to critique, referring to theorems. Okay. And secondly, for statisticians to apply the sample data. You can leave applying it to 100 million data time series to the astronomer. But if you can show us applying it to 2 or 3, and what you learn from it, and why our more naive approaches are weak or even wrong sometimes, this would be very enormously valuable. So some of you are thinking about writing papers, projects, I call them, for this course. Okay, so Jonathan and I chatted for a little bit just before class. Okay, so you can think about maybe, you'll take one interesting advanced method and apply it to 2 or 3 sample data sets or something, or something else, or critique of astronomers' practice, or something else. So I, as I said in my email to you a couple days ago, now is the time for each of you to construct a project. Okay. And I'm your teacher for that, because we don't want to bother the 7 other teachers with that.
Oh, thank you for that. But I think it is important when you pick project topics, somehow connect both the areas. That's what I think will make the difference. And if it is something that would be facilitated by having one statistician and another astronomer,
Okay.
so be it.
Right.
But
If you
that's
choose a topic
important.
that really hones in on a lecture by so-and-so, then that person might very well be a good advisor.
Great. So we stop here.
Okay, thank you, Rick, and thank you, Sumit.
Thank you.